Hi, everyone. Um, Thank you for this opportunity. My name is Chris Barsi. I'm a senior scientist at Brelyon, and we saw all of the slides about the difficulties or challenges or trade-offs of headsets, and so we decided not to have a headset and to just put something on your desk. So what we have are what we call virtual monitors, which are desktop-sized display systems that provide depth and immersion without any need for headgear. And if you sort of look at the bottom left corner, all roads lead to MIT. This has been a technology that's been cooking here on campus for quite some time. So I really just kind of introduce you at a high level to our product, which we call Ultra Reality, and then take you through some of the design challenges that we have, which really are similar to those on wearable devices, except at a different scale. That's the main difference, and then talk about some generalizations. So here's a photograph. It's an augmented photograph of a unit of ours. This is a prototype in the middle that we called Fusion. And really, this is the size of our products. And what you see when you look into this front aperture, right? It's a window. It's transparent. And when you look into it, you see this projected this virtual image. And when you look at it, your eyes are physically focusing to that depth. It wraps around you in a curvature that's designed very carefully, and all of the normal parameters are very high: resolution, field of view, brightness. And here's a little video just to give you a better sense of it. You know, as you approach it, it kind of expands its field of view as if you're looking through a window. This happens to be a multi-layer display, a multifocal display, so you see some parallax effects. And this is one continuous aperture, so it's not like a stereoscopic device. There's not one image sent to each eye respectively. It's one image sent to both eyes. Each eye sees every pixel. We're really excited to be recognized continually by business and technical leaders in our fields. So we're really excited to share the technology today. And really, as I said, we're not a company that makes headsets or wearable devices, as valuable as they are, but we're also not one that's making large-scale projections. We're sort of in the middle. So think desktop-sized monitor, that sort of use case, which gives us a different parameter space for all the same design criteria that you're thinking about. And one way we think about it is, if you think about a TV, we're really approaching the limit of human vision when it comes to resolution. Now, this graph is different when maybe you talk about pixel density, but on TVs, 8K has been around for a long time, and really the gains have been marginal. So this slide really lets us think about something else. Like, what are the fundamental ways we should think about immersion? And to do that, we think about field of view, we think about stereoscopic depth, and we think about monocular depth. But really, overall, what we're interested in is comfort. Like, how do you get immersion comfortably that you can use productively for multiple hours in an operator station or control center or a desktop-sized flight simulator? And the concept we start with is that of a human horopter. So when you're fixating on a point in space, there's a surface that point lies on called a human horopter, which is the surface where your eyes perfectly fuse images or points on that surface. And there's a little bit of flexibility, there's a little bit of thickness to that surface called Panem's fusional area. And that surface really varies depending on the fixation depth. It depends on the periphery versus the central region of your fixation. Very complicated shapes. But it's important to understand this, and we use those shapes, those curvatures, to really optimize our display. So here's kind of a sketch of what a set of horopters may look like. Now, really, they're actually much more complicated. They're tilted vertically. The concavity changes depending on the depth. They're flatter. They're more curved. It's not just a simple, sphere whose radius increases as you go farther away. So we have to understand that. And on top of that, we have to understand the concept of monocular depth. Given a certain horopter or a certain depth or a range of depths, how many focal planes do you need to really mimic a volume? And the number is in the thousands if you want to do this truly, so it's very difficult or maybe even impractical. So we limit our displays to one or two focal depths, but really craft them to map to a human horopter. How do we do that? You can pick your poison. They're all difficult. Right? You can have freeform devices which are expensive. Meta surfaces are hard to scale to the apertures that we want. Thinking about different types of cavities or diffractive solutions also have their own challenges. So the concept we like to use, we think about depth modulation as an infinity mirror. In wearables, this is a pancake system where you have a small depth of two semi-reflective surfaces and light bounces back and forth between them, giving you the illusion of depth. Right? That's what we have. And really, this technique was worked on by the CEO about a dozen years ago at the Media Lab in conjunction and collaboration with the Bowendi Lab using time-resolved imaging. Yeah, if you have this cavity and you have a bunch of virtual, that is ghost images, you can eliminate them if you have really fast time gating to just eliminate the other images based on the time of flight. Of course, we don't have that, so we need to think about other ways to do that. So we experiment with lots of different options. Some of them are easier, some of them are harder, but the goal is to remove those other virtual images and also maximize the brightness to the image and the depth that we want. So we have to think about different types of geometries of this cavity. How do we shape that light, not only to get rid of those virtual images that we don't want, those ghost images, but also to shape that virtual image to map to a horopter. Other problems we have, which are also seen in display systems, are the concept of leakage, right? If you have two crossed polarizers, the on-axis light can be perfectly extinguished, but when you have angled light, then you're going to get leakage. And the reason why is geometrically, that light that's at an angle actually doesn't quite see crossed polarizers. You see something a little bit less. And so you get leakage along the diagonals. So across large apertures, that becomes even more prominent. Something else that's more prominent is the idea of surface effects and surface uniformity. Small defects or rough surfaces give you orange peel effects. And we need new techniques and new manufacturing ways to scale that up and to improve that to larger sizes. So here's a rendering. This is a simulation, a physical rendering of a virtual image. On the right is sort of a toy diagram of how it works. You have a C display panel. It could really be any display panel. We use LCD and OLED in particular. It goes through a cavity, and then there's some profiling optics to shape the light into that horopter that we want. And if you think about this as coherent light, which is not, it's incoherent light, but you're basically flattening a wavefront, right, to make it look as if it's farther away. That's how it works. On the left is the rendered image with an aberration diagram. And here's a video of that. It's a little bit hard to see with the ambient light here, but as you sweep through a focus, the central image is in focus at a different position than the periphery, which means that this focal plane is curved. We have a lot of different use cases. So for example, in an operations center, you're dealing with data critical visualizations, and our device can simulate or render the equivalent of 6 monitors that are stitched together in one unit. So this actually has an added benefit of reducing size, weight, and power compared to those setups. So we have active contracts with the U.S. Army to do this, to put this specifically in vehicles where space is highly constrained. We also are working with the Air Force and flight simulation groups to use this as a test bed for desktop-grade flight simulators. So really, headsets are often studied for classroom flight sim, but the challenge is that people can wear them for not very long time. And so we really need long interaction time that's comfortable and highly usable. So those are some examples. More recently, we've introduced two focal plane systems. So this is 2 different horopters, basically, of depth. So it's a multifocal display system. And the back image is 2.5 meters, and the front image is 70 centimeters, all viewable through that same 30-inch window. And so for us, we're really excited because there are a lot of applications here. One of them is improved flight simulation, where that rear layer is the synthetic environment, and the front layer is a augmented head-up display. And we were just awarded, very happy to announce the Application of the Year award from SID last week. Here are some images. So these are photographs of the of the display content with a DSLR camera. And you can see in the top image and the bottom image, which are focused at different depths, different content comes into view. Here's another example of content. This is, remember, recorded with a video camera, and you can see the content having a front focal plane and a rear focal plane. And here's one more for good measure. And this itself is a design challenge too, because the display does not move with the person, right? It's a fixed display system. It sits on your desk. So as you move around in a visible head box, you have to be much more careful about things like color additivity of the two layers or disparity effects of the two layers. And so that's something that we're actively researching right now. As another extension, because we have these two layers, we are thinking about the idea of generative video streams. So imagine a module, a computational module that observes that rear input video stream, basically looking at your HDMI feed, and then automatically understands the metadata and makes inferences on that, and then generates new content. So we actually have what we call a generative display. So we have this software feed on the rear display. It's just plug and play content, and then our own inbuilt computational module that registers what's going on, and in this case it's making annotations about what window is active, what you can do with those things, making suggestions and the like. One really exciting project that we're working on is real-time depth discrimination. So if you imagine a video game or some movie, and the content is rendered frame by frame on either the foreground or the background, which is learned based on some training methodology. So this is something that is inbuilt into our multi-layer display. So we're really excited to share these results. We're also excited to partner with people who are interested in solving these very difficult engineering challenges and manufacturing challenges. I want to thank all our partners and customers, and thank you for your attention.
Hi, thank you so much. I really enjoyed your presentation. I'm very curious, this is ultimately a human-centered technology. And I'm curious if you guys have started kind of conducting in-house studies, essentially. And if so, what has the reception been to this interface?
We've started that. We've started that, yes, in-house. It's very, very preliminary. But the answer is that it's been positive. And one of the active areas of perceptual research and sort of visual ergonomics is the claim that I'll make that having some layer that's 2.5 meters away is much more comfortable on your eyes. And so near screen tasks aren't as near screen anymore. And so that's something that we're looking into and people are responding to positively, yeah.
And I have a kind of subsidiary follow-up. Have you worked with artists or filmmakers who are used to designing for certain kinds of animated media? And if so, what has their reception been to this kind of new, this new Pandora's box kind of with creativity?
Yeah, we have not worked with such people yet. It's something that we're interested in because it really offers sort of a new window. Imagine a video game where depth is a new game mechanic, for example. I think there's a lot there, as you suggest.
Thank you very much for your nice talk. I'd like to understand your technology. So you have 2 panels. So in that case, I think you need a kind of multiplexing. So this is time multiplexing, or what kind of multiplexing do you use?
So for one display, you have one cavity. For 2 displays, there are a couple of ways you can do it. If you, for example, segment your display, then you do spatial multiplexing. or you can do time multiplexing, but then you have to time multiplex the cavity itself. So actually what we really focus on is how to couple two displays into a cavity.